I wanted to touch bases on things that were discussed first in the first talk, and also completely different to what Julia has been presented in the previous talk, because there will be no quantum computing algorithm yet in the things I'm going to present now. But let me just guide you what we want to address with this polaritonic quantum matter. The idea is basically try to answer the question of, can we deliver quantum matter on demand? Can we modify the properties of materials at will using additional external sources as the drivers of those materials? Then in that aspect, there are two versions of it, which is using light matter hybrids, which are the polaritons. And then there are two fields that has been emerging in the last couple of years, which is what we call QED chemistry and QED materials, which basically address with the modifying chemical landscapes in the case of chemistry, or modifying the properties of materials just by coupling to photons. These are traditionally disjoint fields in which most of the aspects were studied by driving those both molecules and solids by lasers. And the thing I wanted to show you is how those properties can be modified when we use the quantum nature of the photon field to alter the properties of the ground state. Then basically this is going to be most of the talk, is to try to convince you that there is a way to really modify the ground state of those quantum systems, either molecules or solids, by breaking some important symmetries of the material in the cavity. And then clearly there will be no time, but I wanted to tell you that all these can be brought together with the field of twistronics, which is this 2D materials and more heterostructures, and having this concept of cavity twistronics to modify the properties of 2D materials in cavities. I will not discuss the later point. I will basically focus on illustrating two aspects of the chemistry and the material science in cavities. Then, before getting into the applications, let me just guide you a little bit on the theory behind what has been the latest developments that we have made in this description. And then the main concept is that we want to merge the description of fermionic, bosonic systems together, and then basically to deal electrons, photons, and phonons in a quantum mechanical point of view. Clearly, this is a daunting challenge, very challenging task. And then we have to come up with a way of casting the problem in terms of quantities that can be accessible from an experimental point of view. And that's the whole idea of what I'm going to show you today, which is this quantum electrodynamic density functional theory. The idea is, let me guide you a little bit simple. If once you grasp what we want to do is basically to introduce photons and electrons on the same footing, then the phonons is automatically included. And then the main idea is, let's take the approach of quantum electrodynamics in the pure style of scattering phenomena, in which you have one electron and another that they interact by emitting photons. Those photons that are emitted has two components. One is the longitudinal part, that is the one that you know, which is the Hartree term, and the transverse part that gives you this retardation phenomenon. But if instead of working in that Coulomb gauge, you work in this temporal gauge, in which basically you describe the process of electron-electron interaction by emitting and absorbing photons, you have that the Hamiltonian, instead of being a two-body operator, is a one-body operator, is a time-dependent one, in which there is only the coupling via the current and the electromagnetic field that is being created by the emission and absorption of the photon. And that's the beauty of this temporal definition of the quantum electrodynamics. The only problem with this approach in the general set is that has been only solved perturbatively, and there is no ground state in the general framework of quantum electrodynamics. However, if you go, as I will show you in a minute, to the non-relativistic limit, you can prove mathematically that this is not the case, that you can do it fully non-perturbative, and there are ground states. Just to give you something that you all know, if you just change this diagram, which is the emission of the photon and absorption, and you just do a transformation of from the temporal gauge to the Coulomb gauge, basically the interacting Hamiltonian is the one that you are familiar with, which is the Coulomb term that gives you rise to all the electron-electron correlations, and in this case, will add also electron-photon correlation. The beauty of the other gauge is that you can include both, how the electron and electron interact and how the electron and the photon interact at the same footing. Okay, this was the whole idea. Then basically what we wanted is to bring what you know from density functional theory or any other technique that you use to do electronic structure methods in materials and chemistry in the case of the temporal gauge, and describe both electrons and photons interacting at the same level. Then let me just write a little bit the Hamiltonian. In the case of the non-relativistic quantum electrodynamics, you will have, this is the Pauli-Fritz Hamiltonian, which has the standard kinetic energy operator, the interaction, the longitudinal part of the interaction between the electron and ions and the electrons, the photon field, which is just a set of harmonic oscillators that describes the occupation of your photons in your vacuum or in the cavity, and then the interaction between the matter, which in this case is the current, and the transverse part of the electromagnetic. This is a general theory. Of course, it's quite difficult to solve, but has some beautiful mathematical aspects of it. It is that this Hamiltonian is self-adjoint, is bound from below, which is extremely important because then you can do variational principles. Then basically there is ground state of material, which is something that we love because then we can use all our electronic structure method to solve this problem. And there is just one approximation that you need to introduce a cutoff in how many photons you include to renormalize the mass of the electron. With this at hand, you can rewrite the Hamiltonian in terms of something that you are all familiar, which is, as I told you, the kinetic, the electron-electron interaction. And then if you work in the dipole approximation, this is nothing else than Maxwell equations, in which you have the variation of the momentum of the photon plus the interaction, which is the dipolar interaction between the electromagnetic field and the electrons. Then this is the Hamiltonian we want to address. And then at the end of the day, the thing you need to solve is the equation of motion, which is quite complex for the current operator, and Maxwell equations for a set of n photons that you have in your system. Then clearly, this is in principle quite difficult to do. And then our idea is, can we do the following approach, which is do a density functionalization of this theory, which is basically, can I map the electronic and the photonic system into a set of coordinates that give me a one-to-one correspondence between the full many-body description of the evolution operator of the interacting electronic plus photonic system in terms of only three-dimensional quantities, which is the current operator and the transverse field of the photon. This is exactly the same that you do in density functional theory, in which this one-to-one correspondences between the many-body wave function and the density of the current of the system. Then the only thing we are adding is an additional vector field which describes the photon. And this can be studied also if you have here the nuclear current for the electron, nuclear and photon interaction. Then basically this is the setup. And if you are able to prove this one-to-one correspondence, you have a set of self-consistent coupled Maxwell-Constant equations that you need to solve, which at the end of the day, they look exactly the same way as you are familiar and was introduced in previous talks, which is set of n independent, correlated nonlinear equations, differential equations for each of the constant electrons, which is the kinetic energy plus an effective potential, and then nothing else than Maxwell equation written in this gauge that I have chosen here. Then that's the part that you are familiar. Now, you will ask to end up here, you don't need to do this theory of quantum electrodynamics, but the reason why you need to do it is because immediately you realize that this effective potential has a new term that is depending on not only the density of the electrons, or the current, but also on the population of your photon field. And this modifies not only...
There's a question.
Of course.
Yeah, can I ask for clarification? So in this correspondence, so you have a sort of analogon of the Runge growth theorem, but you don't have a constraint search a la Levy.
No, there is no constraint search a la Levy, because in the time-dependent case, when you use time-dependent gauges for the... Oh, what happened? Do you hear? There is a problem, no?
Yeah, we don't see the screen anymore.
We can hear, but we can't see you. We cannot see the screen.
Okay, now comes the problem, as always. Now, do you see it?
Yes.
Yeah.
You don't see it?
Yes.
Yeah. Yeah.
That was good.
Okay, I'm sorry. I don't know what is the problem. Please, my computer. No, what I wanted to say is that in this one-to-one correspondence, let me do it here. Between the electrons and the photons, you do it in the time domain. And then there is you don't need to do this restricted search as Ada Levy, because basically you do it with the time propagation. This is a single, the time evolution operator gives you this flexibility that you don't need to rely on the Levy search for the ground state. You just get it as a stationary solution of the time-dependent Schrödinger equation. This is the big plus. The minus is that clearly you don't have an stationary theory. Basically, it's a time-dependent theory in which you have to look for stationary states that in this time domain. I hope it's clear, but that's the price you pay of working with this quantum electrodynamics density functional approach. However, if at the end you do approximations, which is neglecting the dependence on the photon field, you can cast it exactly in the same way that you can say normal DFT for the electron-electron interaction plus correlated photon field Maxwell equations for the electromagnetic radiation fields that you have in your system. And those are self-consistently coupled. And that's the nice thing, because basically it tells you that the Maxwell equations are being modified by the matter and vice versa. And that's what you have to include in all your exchange and correlation functional. The advantage of working in this field is that the photons by themselves are weakly interacting. In particular, in most cases, they're only interacting at the relativistic level. And then basically the interaction between photons is mediated by the non-linearities in the matter. Then it's likely that you can design good approximations for the exchange and correlation between, the correlation term between electrons and photons, not the exchange. And this is basically what we've been doing in the last years. And then we have good approximations for the correlation between electron and photons. And then the electron-electron part is described at the DFT level. Or if you wish, also I will show you now coupled cluster level. Okay, then let me just guide you a little bit of what are the implications of this for the two approaches, and then please ask me anything that is unclear on the two fields of chemistry and materials. And then I hope all will pop up more clear than with the previous slides. Let me first introduce why this could be interesting and all the physics, and then we go step by step in what we can do with these polaritonic states. Let's go first on the standard approach, which is when you have a single molecular system embedded in a cavity. You have the standard approach. The cavity can be resonant with excitation in your material, and then you have the lower polaritons and the upper polaritons being formed, which is nothing else than the bonding and anti-bonding states that you have in a hydrogen molecule. The distance between the levels is just proportional to the light matter coupling, that in the case of a single molecule in a cavity is very small. It's of the order of 0.1 millieV. And we are talking about something which is very small in general in single molecular spectroscopy. And that was the reason why it was assumed that this type of phenomena for molecular systems in cavity was going not to play any role. However, when you go, as in the quantum optics, to an ensemble of emitters, which is an ensemble of non-overlapping molecules, that effect, which is the hybridization part of the polaritons, gets, just to give you an approximation, is proportional to twice the square root of the number of emitters multiplied by the light matter coupling. Then this increases quite a lot, and then give you the possibility of modifying chemistry if you are working with the lower or upper polarity. However, you have to be very aware that there's n-2 dark states that they will contribute, and then they will hidden the physics that you want to address. Then you have to really target phenomena that is dictated by the lower polariton or the upper polariton in this case of the quantum optics. This was the setup that was known for atomic physics. However, when you just bring the following concept to solids, you realize that in solids you have infinite. Okay, let's take a ferroelectric material. You have a huge number of dipoles being oriented, and those dipoles of the ferroelectric could couple directly to the photon mode of the cavity, and this will give you a huge enhancement of the light matter coupling due to this collective phenomena that you can reach in solids. And that's the nice thing of the analogy between molecular systems and molecules and a solid state that will allow you to address strong light matter phenomena. Then before getting into the solids, let me illustrate 3 cases on the case of chemistry, because I think it's easier to understand, and also you will see what I'm trying to convey to you, because we can do exact solutions for those systems. Then let's take one problem which is very well known in chemistry, which is energy transfer between donor and acceptor molecules, which are far apart. And this is nothing else than the Foster or the mechanism of energy transfer between dipoles, which is dipole-dipole fluctuations, which is the equivalent of the van der Waals forces that were also discussed by Alex in his talk. Then basically these dipole-dipole type interactions scale with the distance between the molecules, and as soon as they are few nanometers apart, the interaction is very weak. The question is, could we enhance this dipole-dipole interaction by the photons in a cavity such that this interaction is distance independent? Okay, then basically there are 2 aspects that you need to do. Is first, we were not going to do modern Hamiltonians. It's not a 2-level system. We have the benzene as this 2 benzene ring. Then we have this cavity in which you have the mode that is made resonant with the HOMO-LUMO gap. This is the part that is a little bit artificial, because then implies, in this case of the molecule, having UV cavities, which are difficult to realize experimentally, but this, to illustrate the concept, is not a problem. Then what we are going to look is the energy transfer mediated by the fact that you have a photon that is resonant with the HOMO-LUMO excitation of your donor, that at the end will transfer the energy to the acceptor. There are 2 effects that you will get. Is if you put the light matter coupling in this cavity to 0, basically is the problem of the molecule in vacuum. And the molecule in vacuum, basically you get this known R³ dependence with the interatomic distance, intermolecular distance of the energy transfer. However, when you include the cavity mode, which is the transverse part of the photon field in the cavity, because the longitudinal part will give you the blue curve, basically the Hartree term, which is nothing else than the van der Waals contribution, then the transverse contribution dominates, at least for scales up to 6 nanometers, and is basically constant over the distance between the 2 molecules. This is a big change because it's few orders of magnitude bigger, and this tells you that you can really control the interaction between molecules mediated by the cavity mode. And this has been also demonstrated experimentally recently. Just to illustrate that this is not an artifact maybe of the density functional change correlation functional that we took to describe the electron-electron interactions. What we did is extend the theory for the case of coupled cluster quantum electrodynamical theory. And then let me illustrate you 3 cases which we all know DFT tends to give you wrong results, which is in the van der Waals interactions on dipole-dipole induced phenomena, which is weakly interacting bonding of water on benzene, or type of hydrogen bond interactions between molecules in biology. I will illustrate you 2 cases, and then the first thing is in the case of this water interaction with benzene, the first thing you have to realize, if you do Hartree-Fock, or you can do your wonderful local or semi-local approximation, you get that the water molecule is not bound to benzene, it's unbound, both in the DFT or in the Hartree-Fock. However, when you go to the coupled cluster level of the theory, this molecule is weakly bound, is PC-short on the benzene molecule. But this curve, what I want to show you is when you go from the dashed line to the continuous line, you see the effect of the cavity. And the effect of the cavity is making this PC-short molecule completely unbound. And this motion of the potential energy surface to higher values is both at the level of the coupled cluster theory or Hartree-Fock or DFT. In the case of the proton transfer, we have similar phenomena, is that when you go from the DFT, from the coupled cluster to the case of the coupled cluster with the cavity, you get a modification of the vibrational frequency and the binding energy. And this effect is also much better captured in this case, both for Hartree-Fock or the DFT and the OAP formulation that is equivalent to Hartree-Fock. Then basically the functionals that we have in many of the cases reproduce those complicated phenomena, and in other cases in which the bond is more covalent in nature or ionic, the interaction is much better reproduced. Then this was to tell you that both, there is no an issue with the level of description of the theory for the electronical interaction, and then this type of approach based on density functional quantum electrodynamic theory give you the right physics. And thus, this is just to give you the main result of a lot of months of calculations. Is some experiment that is very controversial, is the fact that Edison group and other groups has demonstrated that there is a change of the yield of a chemical reaction, which is this deprotection reaction of the phenyl trimethylsilicethylene, which is nothing else than the absorption of the bond breaking of the carbon-silicon bond due to the approach of fluorine to this bond. This is a typical reaction in chemistry that is very effective and is very fast in gas phase. However, the question is whether you can inhibit or stop it or make it slow in the case of having it in the cavity. And that's the experimental result. This is what you have outside the cavity. There is the fragmentation, the reaction always happens when you have the cavity resonant with the carbon-silicon vibration, then you get an effect which is the quench of this product and the appearance of this other in much higher yield than in the case of the gas phase. And then if you are off resonance, basically you reproduce more or less what you did have outside the cavity. Then there is an effect which is resonant, and then the yield is being modified. Okay, then this is one of those cases in which if you try to do simple models or semi-empirical models, you are not able to capture, because this is linked to the modification of the ground state of the chemical complex, which is this complex in the cavity. And then what basically happens is that this potential energy surface, which dictates how you go from the reactants to the products, is being modified by the cavity mode. And the physics is extremely simple, maybe too simple, because it's at the end of the day realize that it's just a question of opening channels for energy distribution. What happens is in the gas phase, to make the story short, if you compare here the red curve or the black curve, which is the time that the fluorine atom stays close to the silicon carbon bond, you see that in the normal gas phase it stays little and then immediately breaks the bond, and this is what it's doing. But in the cavity, which is the orange curve, stays in that area of the carbon-silicon bond for longer times, which makes the reaction going slower. And this is nothing else that you open new paths for energy distribution of the bond breaking of the carbon-silicon bond into other degrees of freedom that are activated by the cavity. This is the nice thing. Of course, to do these calculations, we did an artificial strong light matter coupling, because we were dealing only with one molecule, one reactant and one active fluorine molecule. But this effect will be enhanced if you have many active materials. Okay, this was just to illustrate that, at least in the part of chemistry, that you can cross-check with a high-level theory that the theory is working, that we can get the description of the electron-electron interaction with photons properly. Then let me just go to the materials, and here is where I want to spend a little bit more time and guide you to the main concepts of two aspects. One is Floquet and the other cavity materials engineering. Let me introduce the two concepts and let's see if I can convince you that they are equivalent. Okay, let's first introduce Floquet. And then what we are going to have is a quantum mechanical system that is going to be excited by a photon. Then basically the photon is fluctuating with the frequency of the light field. You can all as well think that you have the electronic system that is modified by the phonon, which is addressing electron-phonon mechanism or dissipation due to the phonon. Or you can as well think of plasmons, which will be capping your electron to a plasmon. Or you can think of any other type of bosonic excitation that you can have in your system. All of them, they share something in common, is that from the perspective of your electronic system, those perturbations, they are time periodic, with the periodicity of the photon, which is the electromagnetic field, the phonon, or the plasma. No? And if you have a time periodic driving field, you can write the equation of motion as a stationary solution, which is basically Floquet theory, which tells you that in this stroboscopic approach to quantum mechanics, you can have eigenstates that will be, let me highlight what it looks like. You have this valence to conduction excitation. Basically, you put the photon field, which is resonant with this one. They overlap because you make replicas with one photon or minus one photon. And then the interaction between the valence and the conduction band give rise to an opening of the gap, which is the AC Stark effect. And this band gap opening tells you that you can open it here, as I did at the bottom of the conduction band, but you can open it everywhere in the two-dimensional or high-dimensional viewing zone that you are interested in. And this is nothing else than stabilizing a material due to the fact that you have something that is driving the system, driving the system periodically. Then you can think of that field, which is driving the molecular system, either in the Floquet picture, which is some sort of wave that is moving your system, or in the cavity, because in the cavity you have exactly the same modes that is acting on your material. And that's the analogy between what is Floquet engineering, which is light-driven phenomena, and optical cavities, which is quantum fluctuations mediated phenomena in material science. Then to tell you that, at least that you believe that I'm telling you something that makes a little bit of sense, let's take the many-body wave function and expand it, in the case of Floquet engineering, in eigenstate, which is a Fourier series of your driving frequency, which is nothing else than this expansion in Fourier series, and then you plug that wave function in the Schrödinger equation, and then basically give you a set of eigenvalues and multiples, which is +1, +2, +3, or -1, -2, -3 replicas of that band structure with the photon acting on the wave function, and then the coupling, which is in the dipolar term, give you the case that you couple with +1 or -1 photon, or +2 and -2, which is the diamagnetic contribution, which is the A² term. That's the Hamiltonian that you solve in the case of Floquet. In the case of cavity, you can do the same many-body expansion. Instead of having the Fourier analysis, you have the modes of your cavity, which is in focus space written this way. And if you plug it again in the Schrödinger equation, you get an equation, a differential equation, that it looks very much the same as the one that you have for the case of Floquet. No, it's only that you have the 0-point motion that you don't have in the case of Floquet theory, but all of the other terms, they look very much the same. You have the connection to the +1 and -1 sectors, and +2 and -2. Then this tells you that if you are able to generate by light a non-equilibrium state, there is quite a good chance that you can set up a quantum electromagnetic environment that will reproduce that driven phenomena as the ground state of your interacting system. And that's just to illustrate that this is in the case. The Floquet Hamiltonian and the QED Hamiltonian, they share a structure which is bounded, is tri-diagonal, and is quite similar. That's something that you can assume there is an analogy. Of course, you can prove that there is not exact, because as you can see, the QED Hamiltonian is only one part of your Floquet Hamiltonian, which is the positive part, because it's bound from below, whereas the Floquet Hamiltonian is unbound from below. Okay, this basically is something that we have proposed, that there is an analogy between Floquet and cavity. And the idea is that you can control quantum vacuum fluctuations to design non-equilibrium states of matter that has been reproduced to exist, or has been shown to exist in PAM probe light matter phenomena. Then basically, just I want to give you, this is what you have is on the left is Floquet, in which you have potential energy surfaces that are dynamically moved, and then this is stabilized by the perturbation. Or the other case, which is in the cavity, where you get is some sort of Mexican hat type phenomena that dictates that the system is stable. And this phenomena that is temporary and just a metastable solution in the time domain becomes the ground state of this quantum phenomena, which is in the cavity. That basically looks like that what you have in superconductivity with Higgs modes, with the phase and amplitude modes in coupled correlated systems. And that's the analogy that we want to use in order to define correlated phenomena. Okay. Then let me give you two cases, and then I hope I will convey to you that this is clear. Is something that has been proposed many years ago by Oka and Aoki, which is the fact that if you take graphene, that you all know is a Dirac material, if you come with light, which is circularly polarized, basically you open a gap, which is proportional to the intensity of the light field and inverse proportional to the frequency of the applied circularly polarized light. And then this basically makes, as a transient state, a semi-metal into a topological insulator. And this has been one of those things that has been predicted by this Floquet theory, and in fact has been also realized in part by light-driven phenomena in graphene. And this was demonstrated by James McIver in Hamburg with very interesting experiments on transport, which I will show you here now. What he was looking is what is the conductivity, the transport change when you have left-handed and right-handed light. The difference between the two will give you the contribution from topology, which in this case is the very phase, and that's what they saw, which is the current as a dip and then a plateau every time you have a gap opened by the Floquet band gap engineering. Then this is the fact that you indeed have those Floquet states, that you can realize them. To realize them, you need to include dissipation. I will not describe you this in detail, but this is basically what happened is that the contribution to this current has an effect which comes from the population of the bands, and an effect that comes from the very curvature, which is the topological part. The one that is dominating and in those conditions is the population imbalance induced by the electromagnetic field, but at the end of the day, you can see that there is a current being generated. Okay, that's nice, because basically what you can think of, now I could have a cavity that generates the same type of phenomena by having chiral mode. Okay, this was one idea. I will show you later that that's the case. Another thing which I think is more interesting to show you is what I show you in the previous slide is if I take graphene, which has a Dirac semi-metal, I make it into a topological insulator by coming with circularly polarized light. This is known. Then let me show you how this can be. This is done with the circularly polarized light. But now what I can show you here is how much I can populate the lower or the upper state. And I can basically do optimal control theory to say that I want to populate only the lower one or the upper one, which will be Chern number +1, Chern number -1. The laser field is what I'm plotting here. And this is the population of the state, which is the occupation of the bottom state. And then you can see that goes from half-half, because it's a Dirac cone, to something that is fully populated. Okay, this is something which you would expect. That's something that is interesting, because then you can say that you can really go from the semi-metallic system to a topological insulator. But this was predicted. And why I'm telling you all that is because now what we can do is something more. We can put as a target of our minimization, instead of being opening the gap, is having flat bands. No? Having flat bands through up 10% of your Brillouin zone. Okay? And then basically this is what we did. And then if you do an optimization with only 5 frequencies, you can really reproduce that the band, which are the blue ones, the minimized ones, which are in the cavity, they really match and they get flat as you wish. And this is the shape of the pulse, which has frequency omega, 2 omega, 3 omega, and 4th omega. Then it's only few harmonics of the driving frequency. In the other case was the circularly polarized light that I told you that opens the gap. And then here you can control the size of the gap by the relative phase and then the length of the flat band by how many omegas do you include in your driving field. The beauty here is that you have flat bands in a single layer graphene structure. You can as well ask yourself whether you can change the curvature and then go from positive to negative. And indeed, you can do that. Then this tells you that there is a way to manipulate the electronic structure, not at will, but quite strongly by just modification of the relative phase of the electromagnetic field. And the reason why I show you that is because you can think that if I have a cavity that is populated, the mode 1 with this intensity, mode 2 with this one, and mode 3 with this one, I will be able to generate exactly that flat band as the ground state of graphene in a cavity without any external driving field. Then this is what I wanted to tell you, which is basically how to mimic the structure of the graphene and modify it. Then now you can add as many additions you want. And then let me show you something that I found quite interesting, because first I thought was wrong, but I think is quite interesting, is if you have two lasers equally polarized with omega and 2 omega, each of the lasers has inversion symmetry. And then you don't make inversion symmetry, and they have this chirality. But at the end of the day, they are also time periodic. However, if you do the sum of the two with a phase, you dephase them, what you get is this type of energy profile, electric field profile, which is the Lisa-U curve. And this curve is all of the sudden has a symmetry in the X plane and not in the Y plane. Okay, which basically introduce an spontaneous breaking of time reversal symmetry due to the chirality of the field plus inversion symmetry break. And this is nice because with those fields, which will be generated in a cavity, what you can do is the following. You can take diamond and apply exactly this field for this short period of time, which is 8 cycles, and then look what happened after you apply those laser fields that has broken inversion symmetry and time reversal symmetry. And all of a sudden, what you have created is galvanometric effect, which is a net current in your system. And this is what is being done usually in photogalvanometric materials, which is materials that has intrinsic symmetry breaking of the time reversal due to the spin-orbit coupling, plus the inversion symmetry breaking due to the structure of the lattice. Then you can take a system that has none of those symmetry broken in the ground state and make it behaving as the other ones that has those symmetries. And this is general because you can do it both for silicon. Basically, this will be in the language of photovoltaics that you are generating shift currents. You can do it in magnesium oxide, or you can do it in hexagonal BN or any other system. And it's independent whether the system is insulator, metallic, or semi-metallic. Then this was something I wanted to tell you, and probably I'm running out of time. No? Then just to conclude, I wanted to show you that this was for driven systems, what are the properties, and then if you just do exactly the same, now it's repeating the things in the cavity, you can control the energy position of the excitons, which is something you can have into the materials in the cavity. Just to illustrate you how it looks like, this is the interlayer and intralayer exciton, how they look in the vacuum. And then if you just plot them as a function of the strength of the light matter coupling, you can see that you can go from this ordering of the excitons to exchange of the inter and intralayer exciton. And in fact, if you can keep increasing the light matter coupling, this can become the ground state of your system. But this is an excited state. And then something that I found, this is new, and that's we did exactly the same in a setup which is quite interesting. Let's take a 2D electron gas when you apply a magnetic field, and then you have current going through the system, you have the Hall conductivity, and in that setup, forget about the mirrors, you get the quantum Hall effect, which basically is that the resistance or the conductivity is proportional to the occupation of the Landau levels, and is basically proportional to E squared over H, no? With an integer number, which is the integer quantum. the integral quantum Hall effect, and that's quite robust. If you do exactly the same calculation, which is, by the way, analytical, it takes only a few lines, and you solve this problem of a constant magnetic field with a constant electric field that drives the current through a two-dimensional perfect 2D gas, then you can prove that the Hall conductivity is exactly the one that you would expect in the gas phase outside the cavity, and is renormalized by G squared, with G being the light matter coupling. Then, just to make you the story short, the well-known quantization of the Hall conductivity in a cavity is modified by as much as you wish, depending on the light matter coupling. Let me just tell you that most experiments, the electromagnetic field is of the order of Tesla, the cavity field is very small, and basically you are in this regime, then you don't see it. But there are recent experiments done by Jerome Fais at ETH, in which he is seeing the modification of the quantum Hall, integral quantum Hall effect in the cavity. And those were just to give you ideas of what you can modify. And the last thing is, all that were modifications of excitons with light, modifications of the quantum Hall effect with magnetic field. And what about what I promised at the beginning, and then I promise I finish, is the ground state of a quantum material. And just to make the story short, what we took is STO. The reason, because STO is a quantum paraelectric, that as soon as you make it strain or you change the temperature, you can make a transition to a ferroelectric, and there are different perturbations. Then it's a system that is close to a phase transition if you just drive it. And then that's what we wanted to do, and then has been also demonstrated experimentally by two groups, Andrea Cavalieri and also Kit Nelson, that if you drive STO, you can induce the transition from paraelectric to ferroelectric transition due to the coupling of the electromagnetic field to the soft mode of the STO. Okay, that's what they did. And then taking all that into account, what we thought is what happens if we make a cavity that is resonant with this phonon mode that is being pumped in the terahertz region, which is quite easy to do. I will just tell you now what we have is basically what we want to do is what they come is with the light and induce a phase order. We want to do it with the cavity. Okay, then to make the story short, I will skip how we did it. And this is what you will end up getting is that as you quench the light matter coupling in your cavity, and this is a question how to do it experimentally. This is an open issue that you can go from the quantum paraelectric solution that is known at T equals 0 to a ferroelectric solution, which is the STO being located in one or the other of the two wells of the STO. And this is being seen as another way is that the phonon that connects the soft mode is being made softer by the interaction with the quantum cavity in this case. Okay, this was just to illustrate a particular case that you can really induce without electromagnetic field a phase transition in your system. And thus, to conclude, basically what you have is to the normal temperature and pressure phase diagram in which you have the quantum paraelectric to paraelectric transition. You can have as a function of the electromagnetic coupling, you can have a quantum paraelectric to ferroelectric transition, or the standard one, which is paraelectric to ferroelectric. Then I think this is to tell you that you can add to the normal phase diagram of your materials another line, which will be not only the temperature, the pressure, or other disorder, but also the light matter coupling. And with that, I want to conclude, and then I hope I convince you that there is a new interesting field of cavity and Floquet materials engineering, that we have a theory that allows you to do first principle simulation of those coupled systems of electrons and photons and phonons, that there is an interplay between collectivity, how many interacting systems you have, and locality in the case of chemical reactions, but this Polaritonic coupling is also important for solids that will give you strong light matter coupling, and basically that you can generate new Polaritonic or quantum phases of matter as ground state of your material embedded in a quantum environment. And then this is basically what I wanted to tell you, is that at least the take-home message is that use quantum fluctuations and strong light matter coupling, okay, which should be electron phonon to control electron phonon correlations. And if you wish, you can do either quantum Hall phenomena, you can aim to address if you can topology or superconductivity. And then this is the people that did all the job, both at the Flatiron Institute, and in Hamburg, and then all the people that has moved to University of Penn and Aachen as permanent. And then, yes, with that, I want to thank you and just apologize by taking a little bit longer than expected. Thank you very much.